try to give you 6 targets, but you only have 5 joints, what are you going to do? So the general theory actually talks about you can have cost functions, weighting parameters to try to balance all of that and minimize it. But to me, the much simpler version is, and this is what I just want to make sure that we're clear, is define custom 5 DOF, that's what it is, coordinates. Right. Rather than using the general 6-dimensional position and orientation, I want to define 5 DOF, because then, right, you guys agree you can specify this more correctly. So certainly X, Y, and Z are probably going to be, I shouldn't say certainly, probably, right? Very likely X, Y, and Z are going to be part of the coordinates, because you're going to try to reach for an X, Y, Z place. And you can take it directly from that calculation. So the calculation is not lost. You can use those X, Y, Z. Did it make sense talking about kind of a theta and phi? So I like the idea of that being the horizontal angle, or I guess the up-down. Right. So if I have a mechanism, then I think of it as kind of the angle of the tip from horizontal. Because for a lot of things, I think that's kind of a useful thing. So for example, you might have the theta, which is Q1 plus Q2 plus Q3, if you have kind of that type of mechanism. Did that make sense? The other one that I tend to use is basically output roll. And the only comment is that if this is horizontal, this is with respect to the horizon. But if theta is vertical, i.e. you're pointing straight down, right, this is going to be with respect to the world frame. So you got to be a little bit careful in how you define it. But one way that we talked about that works fairly well is to basically do something silly like this, right, where you change the definition slightly based on theta. Does that make sense? So the name of the game is basically defining these. Once you've defined the 5 DOF, right, the IKIN becomes solvable. And I just want to make sure that we're in agreement on that and kind of what this means, because I think I rushed through that a little bit at the end. For 4 DOF, it's one angle. It's fairly clear. 5 DOF, these tend to be, but this isn't the only option, right? You can do other things. For example, if you're basically your end effector is a pointer, so you're not rolling about the output, but you're pointing left and right, then output roll isn't really a useful thing. So alternately, if you're pointing, right, you may use a normal vector, which is just the vector that you're pointing to. So for example, you could say that n vector is just, let's say, the z-axis of the tip expressed in world coordinates, right? If z is your output vector, that would be the one. Which means I can grab that from the R matrix if I want. Does that make sense? So if you're holding a pen, and I have to admit, I'm not entirely sure if that's what's going on in that team, but I mean, if you're holding something that is pointing left and right and not spinning, that's probably the one I would use. So the point is, these should be meaningful kind of to your project, to your task. Obviously, I want to be able to specify this is what I want the thing to do, so they should be meaningful to that. Does that concept in general make sense? So half of the name of the game this week and in the homework is to basically say, what is the set of coordinates that is most useful for your project that is 5 degrees of freedom that you can specify the state of the robot in nicely so that when you convert it back to joint space, it makes sense. Thoughts, questions? I know I went a little bit fast at the end last week. I just want to make, on Monday, I just want to make sure that that's clear. So I definitely want to, we talked about the IKIN then being solvable in an analytic sense. It gets ugly. The math and the geometry is kind of annoying. So I definitely want to talk about kind of the numerical solve for it, where you just write the algorithm and let it converge, so you don't have to deal with it. For folks that don't want to write the math out, right? Before I do that, let me do one thing and and talk about grip. So there is an age-old debate. Is grip part of kinematics? Or not? Do you consider grip a separate thing, or is it part of your robot's configuration? And in the end the answer actually, you can pick whatever you do. Some people argue very strongly one way, and some people argue very strongly the other way. My comment is that as a joint, my grip joint is going to be the angle of the spool, right? You guys remember that the gripper basically is the pull cable, so the grip motor is basically a 30 degrees on that spool. Well, that number doesn't necessarily mean that much to me. If I'm telling the gripper to go over and grab this block, right, what does 30 degrees on my spool mean? So you could argue that a Cartesian version or a tip version of grip could be the distance between the fingers. So something like 0.0 meters all the way to, I don't know, 0.1 meters, right? And especially if you're thinking about what is the size of the object you're picking up, that's probably a useful thing to specify. If all you want to do is specify open and closed, maybe you just do open closed and have this go from 0 to 1 without any units, right? 1 being open and 0 being smack closed. It's the same thing as distance, except you don't even bother figuring out what the distance is. Degree in either case, I could say G is going to be some slope times Q of the grip, actually write that correctly, minus Q offset. Right, there's just some constant, and you can calibrate what that is, right? Just open and close it, and read the values and figure out what that number is. So in that sense, you could argue that my custom coordinates are actually x, y, z, maybe those two angles, whatever it is, and grip. Right, so then you end up kind of with those 6 parameters. And so the question is, do you carry grip around with you? And a lot of times I feel like it is easier. It defines the state of the robot. And it's either the state of the robot in joint space, it's all the motor angles, or the state of the robot in tip space is the position and orientation and the value of grip. So personally, I a lot of times include it, which means my kinematics now has one more element in it. Does that seem okay? So all of that said, is what I'm asking on the software side is basically, 1, define the coordinates, right? And so that really means you probably want to define a Ross message type. Remember, like in homework 2, you define a Ross message type for pitch and yaw? So now define one that is x, y, z, theta, phi, and grep, right? Which is your tip coordinate. That means you can have an fkin function which takes q, and you might as well produce r, x, and r because they're great to visualize and look at, but also produces kind of the tip coordinates. And then hopefully that is kind of still what we have. The new part is an ikin of q, ikin of tip that produces q. Right? And I'm deliberately doing it of tip, not of x and r, because that avoids issues of kind of solvability. And if I'm picky, I might do tip, comma, branch option, if I want to specify which branch I'm on. But probably you're always on the same branch. Probably you're just in front with the elbow up, right? Most teams aren't going to try to put their elbow down and hit the table. Doesn't really make any sense. Maybe you've got a situation where you do want both branches with the branch option in. Or make it tip, comma, q example. Where by that I mean give it a joint values and basically say stay on the same branch. Right? Meaning if I had a previous solution, or I'm kind of over here somewhere, well, use that as your reference to kind of figure out what branch you're supposed to be on and use that. Does that make sense? So the way that it then to me looks is I take my heavy node, out comes the actual joint, in goes the command joint. Right? I can stick that through an Fkin to get my XR, my tip, which I can visualize. I can put into RViz. And I can actually do the Ross Fkin as well if you want, and stick that into RViz and get kind of the nice pretty drawings. I also stick that into Fkin and get out a tip. So now it is a tip command. And then in is, let's say I give you a joint goal and ask you to do a joint move. Do you agree that basically that is going to go through a trajectory generator and produce kind of the commands? And by this, I'm thinking exactly what you guys did in homework 2 or 3, can't remember which one it was. Right, do a trajectory generator through a goal. Meaning you're effectively having a message handler that receives the goal, calculates the spline that you want, set the spline, and then there's a servo that spits out at 100 hertz, kind of what that is. Does that seem reasonable? Very similar to what you did, except instead of 2-dop, it's now 5-dop. Instead of pitch and yaw, it is now, in this case, a set of joints. Yes?
Calculate the step command purely for checking.
Yes. Sometimes I do step commands. Step commands basically make the entire system shake, and so that's sometimes a useful thing. When you're running the robot, I don't want them. I want everything to be continuous. Right? And so it's one of those, it's a useful debugging tool to shake your system and see what rattles loose, but it's really only for debugging, not for running. Does that make sense? Yeah?
What is the branch option? Is it normal that you always operate on one branch?
So normally you operate on one branch only. There are cases where maybe you're reaching and then you need to reach over behind you or something, where you might want to switch to a different branch for a particular scenario. It is more likely than not that you won't do it. So it's more likely not that you will always be on the same branch, in which case you might as well just leave it always on the same branch, period, and never change.
Do you then need to write the option into your code?
So if you want to be general, you write an ICANN that takes a branch option. And you always pass it the same branch. And just say always be elbow up and always be in front of the arm and whatever it is. Right? And then if you want to, you can use a different one. So you could then sit there and move down and do kind of, but I mean, realistically, you probably won't need it. Yes?
In this example, the icon's not drawn, right? The trajectory generator operates in joint space.
The trajectory generator is in Q0 to Q5 kind of a joint space, and I'm going to include grip in it, yes. So what I then mean is, if you give it a tip goal, but do a joint move, right? Then you would stick that through an ICANN, and then stick that in here.
Okay. Would it potentially make sense to make those two nodes the same if you want to, for example, be
Yes.
continuous in tip space?
I actually think of, you're completely get ahead of me. I actually will, you're absolutely right, do, let me get a real color. I like, is I would put all of this in one node. Let me finish the drawing and then kind of come back to answering that question, but you're absolutely right. Does it make sense that I might do either one of those? I might find the final goal, convert it into a joint vector, and then just do a trajectory and joint. Or option 3, and I've asked you kind of to do all 3, is to do a tip goal with a tip move. Right? But let me get this for a second. what I would do then is basically stick that through a trajectory generator that now is interpolating x, y, z, theta, phi, and g. And then stick that through an ICAN and stick it in here. Where I mean this is the handler side. So the handler once sets up this trajectory interpolation the same way it did for the joints it can set it up for these, right? They're just 6 variables. And then basically the ICAN has to happen at every single point along that trajectory. So that the ICAN is then part of the servo every single time. Which means you now have a mode kind of in here. Am I doing a joint move or a tip move? Right? And the servo loop is either going to take the parameters from the joint move or the parameters from the cart move, the tip move, depending on which mode you're in. And that is why, yes, I think of all of this as one node. Now, for this week, don't try to make the code super fancy, right? I mean, if you want to try 3 different test cases, write different test cases, and that's okay. But in general, you can't simultaneously do a joint move and a cart move, right? It doesn't make sense. You can either do one or the other. So having it in one and the same node means you can have one and the same node, means you can have a mode flag, which selects which one it is. If you put these into different nodes, you can't turn a node on and off very easily, right? It doesn't really make sense. So I think of this as my trajectory generation node. And it can either take a joint goal or it can take a tip goal. And whichever one it gets, it internally switches to that modality of running. Does this diagram make sense? So I want to talk a lot more about kind of the inverse kinematic numerical solver, but this is what I'm asking you to do. If this doesn't make sense, we're kind of lost, so please.
But do you need all 3 of them, or do you only, for example, the first and the second one? If you get
I just fundamentally didn't hear the first part.
Do you need to implement all 3 of these options? Or
You certainly want this one. This is the safe one, right? You just go to a joint coordinate. For example, you go to your home position. There's no kinematics, there's no singularity, it is just a joint move, it is safe, you always want that. You do want some version of the tip goal, because you have to go grab an object, and you want to specify that object in XYZ coordinates. Now the question is, do you want both a joint move and a tip move? These are a little bit redundant. The top one is almost trivial to implement, right? Because all I do is I call the ICAN and then I stick it in. So this is almost a freebie. Not quite. Nothing is ever free, right? But I mean, it's fairly easy. However, the bottom one, do you guys remember we did this drawing that if I have my starting position be this, so this is my start, and if I give you a final that is here, right, then my final solution looks like that. If I do a joint move, then I'm going to hold this joint and I'm going to move along this line. If I do a cart move, I'm going to go up here, which means temporarily I'm going to pull back as I'm doing it. So if you are a team that is drawing on a piece of paper and you want to draw a straight line, or if you want to grab something from the table and you want to move straight up from the table, you probably want the ability to move in a straight line. Which means you have to basically interpolate the x, y, and z, and then solve the ICAN in each one. So there's a really good chance that you want the third one. The second one you may or may not want, but it's easy to do, so you might as well do it. So the short answer is I would actually recommend having, maybe not for this week, but ultimately a node that has V3's goal options. And whether you make it one goal topic with a flag that tells you which one it is, or whether you just make it 3 goal topics, we can talk about all of that kind of, and you can implement it however you like. But does it fundamentally make sense? I can ask the robot to do one of these 3 things. I can't simultaneously do both, right? Which is why I put it in one node. And the node will then be in whatever mode it's in. Any other thoughts on that? I mean, this is the framework where basically I go from goals, which is all my high-level behaviors are going to say, go here, do this, do that, right? this is how I get the robot to execute those and generate the commands I send down to the head. So this is kind of at the core of everything we're going to do. So I realize, just to kind of say it out loud, right, I realize there's a lot going on, there's other classes. I'm asking you to build a mechanism which is a 5-6 DOF mechanism, right? I'm asking you to implement the inverse kinematics and all of it. So I realize I'm asking a lot. If this isn't fully operational by Friday, I'm not going to penalize anyone for that, right? I want to keep pushing because this is important and we need to get this straight. So my hope is that it works. If it doesn't work, we will iterate on the mechanism, we will iterate on the bugs and debug it kind of going forward. But as what we're trying to do, does that seem like a reasonable picture? So if that's the case, the piece that I want to then kind of come back and kind of work a little bit more on is the IK using just a numerical solution rather than having to do the math. I'm going to leave that one up on the side. That is kind of the framework that I'm trying to put together. And all of it is built around kind of this idea of the custom coordinates that make sense to your mechanism. Okay. So, with all of that said, let me do numerical IK, which just means we need to talk about a Jacobian matrix, which means we're talking about differential solvers, which is something we haven't really talked about. So if I do a random drawing and I say this is my joint space and this is my tip space, which is a 6-dimensional here and a 6-dimensional here, so there's no way I can draw this, right? But do you agree that basically this is repeating? Well, let's say it has kind of some pattern like this to it, right? I'm not going to deal with the wrapping. I mean, you guys agree that if I just add 360 to my mechanism, I come out the same, right? Okay, fine. Let's just not do that. Just not wind out on cables. But basically, the idea is I give you some desired, and the question is, you've got multiple solutions, multiple branches, right? What are my solutions here? Any old numerical, take an initial guess, right? Put a guess in, evaluate it, follow the slope down until you hit the target, right? So Q, X, let's say I have this shape, this is my XD, I have my guess. Do you agree that basically I get some delta X? I kind of get a slope M, which means I get a delta Q, 1 over M times delta X, and I get a new guess, right? And then iterate from there. Good old Newton, what is that, Newton-Raphson? Whichever that one is. I forget which one they're named. Right? That's all this is. What that means is, here, I'm going to write it over here, is the algorithm is basically have an initial guess if basically Qi is your guess. Compute the error, delta x, right, which is xd minus x of Qi. Calculate the Jacobian, which is dx dq. And that's what I want to talk about in a second, right, the Jacobian. But then, do you agree that Qi plus 1 is nothing other than Qi plus J inverse of Q, this is a function of Q, times the error? Right? Does that make sense conceptually? So the subtlety is, A, let's start with the easy one. What's your guess? If you think about this, if I put a guess here, I'm going to go to this point. If I put a guess here, I'm going to go to this point. If I put a guess here, I'm going to go to this point, right? So your guess should be close. What that means for us is that the guess is basically how you end up picking the branch. If I use a guess that is far away, you're probably going to end up on a different branch. So point 1 is take the guess. And that is really, it should be, quote, close by, which really means on the same branch. So if you have no idea, take the middle of your workspace with your elbow up, right?
Should it like, can we take the current position as guess?
That is the next best good thing. If you already are somewhere and you want to be near it, use your current as your best guess for what it is. Absolutely, right? And so if you have no guess, right, take the center of the workspace on the right branch. If you have a guess, right, then take the previous position. So you can find usually a pretty good guess. So, okay, done with that topic. So the big question is, how do I get the Jacobian? With me on that? So, I should say, repeat. Let me just put it up here, right? And you can either do a finite number of iterations, or usually, literally, people look at the size of the error until that is, quote, quote, small. And you can argue what small is, but small is probably within a millimeter or something. Or maybe within a micrometer, in which case it's really, really small. So, actually, let me make one more comment on this. Let's say I give you a function like this, right? And I give you a desired up here. I pick my initial guess here. Well, I'm going to project that. Oops, fine. I'll fix my curve so that works. Right? I'll pick my here, which means my next guess is here. So this is I plus 1. But that kind of shoots back out here. So these algorithms are nice, but imagine that you take your robot. Let me draw it. And this is just as a quote, quote, matter of warning. Imagine that this is my initial guess, and my goal is out here. Well, that means I need to move in this direction, right? Which means this guy is going to rotate this way, and this guy is going to rotate that way. But if you have that kind of thing, if you're not careful, you're going to overshoot. And you're going to end up in this configuration. And then this guy is going to go that way, and this guy is going to go that way. And if you're not careful, you bounce back and forth. And if you look at what you've done, you've jumped over the singularity. Right? And so all of these things is be careful. Depending on what your goal is, depending on what your guess is, you can end up in ugly configurations. And it's very hard to say exactly when that's going to happen. So one thing that people do here is before they take the inverse, right, is to check for singularities, to check how close you are to singularity, in the hope to kind of get around this problem. But the short answer is avoid singularities and kind of make the goal reasonable. Which isn't really very useful, and I don't know a better way of saying it. And that's the problem. This is why I sometimes vote for doing the analytic solution. There are situations where as much as this algorithm looks really nice, it can go completely nuts on you. And it's very hard to predict when that's going to happen. And so you're moving along and you give it a random goal, and all of a sudden your robot does crazy things. Right? And so when that happens, turn it off. So that is just as a random comment. Things can go nuts. But assuming that we're in a location where you start here and you're moving over, right? So you're doing a small, quote, move. It should be fine. So let's talk about the Jacobian. you guys agree J is basically the set of partial derivatives, which means dx is equal to J times dq. And I try very hard to write J of Q because the Jacobian obviously changes based on where you are. I shouldn't say obvious. The Jacobian changes based on where you are. It's a function, right? Do you agree that that also means x dot is J times Q dot? And a lot of times that is easier to think of. So if I take my really stupid example, do you agree that xy is L times cosine Q and L times sine Q? Do you agree that x dot, y dot is minus L sine Q, L cosine Q times Q dot? That is the Jacobian. Note it is, in this case, 2 by 1. Right? Where I have one joint, but I've declared my output to be 2. Clearly, if I do a 2 by 1, I can't do an inverse. This is why I'm trying to get us to have 5 coordinates for 5 joints. So the Jacobian is 5 by 5, so that you can invert it. Right? So the Jacobian is basically the cart DOFs, the tip DOFs, times the joint DOFs. Kind of as a matrix. So, how do I generally calculate the Jacobian? This is what I want to get to. If, let's get rid of that. If I draw my general purpose robot, do you agree, for example, if I look at the base axis, that if this guy spins, this tip is going to move into the board? So what I think about is if x dot is equal to j q dot, then really j is a set of vectors times q0 dot, q1 dot, q2 dot, etc. Or this is effectively j0, j1, j2, right? So the Jacobian matrix is columns of what happens if I only turn j q0. What if I only turn q1? What if I only turn q2? Right? Those become the columns of j. Make sense? So, in general, right, for the 6-dimensional case, what you think of x dot is you think of it as linear and angular velocity. Right? Linear velocity is 3, angular velocity is 3. Which means, in general, the Jacobian is a jv and a j omega, right? Which is my linear and my angular. And if I go back to this picture, I am going to basically do the following. Assume that you're walking up your kinematic chain. This now comes all the way back to the beginning of the kinematic chain. So if I have right here joint I, do you agree that you have an xi given world frame? At some point you are computing this location. Do you agree that you had an Ri with respect to world frame, which is nothing other than an Ex, Ey, and an Ez, right? With respect to world, with respect to world, with respect to world. So I can also pull out of there an Ei with respect to world, which is, quote, my joint axis. So if you're walking up the kinematic chain, do you agree that I can find this location and I can find the vector that is my joint axis. I can also eventually find out what is the tip. So here's the tip. Do you agree that the linear velocity is EI with respect to world cross x tip minus xi with respect to world? So imagine here's an axis of rotation. This is x tip minus xi. Right? So cross product. Vector things gives me the linear velocity at the tip. So the short answer is a particular joint I adds a tip velocity that is just this cross product of the joint axis times the distance to the tip. So the process means go through the kinematic chain. That's one of the reasons I wanted to do that whole Fkin is you go through the kinematic chain. Remember where where the joint is and what the joint axis is. And then basically that is the element in the Jacobian matrix. The angular one is even simpler. It's just that. Because if that joint spins, do you agree that the tip spins with the same angular velocity? Which means, in the general case, and I'll get to the custom case in just a second, in the general six-dimensional case, my Jacobian becomes this J0V, J1V, J2V, right? J0W, J1W, J2W. Which means it is 6 by n. And usually n is 6 as well, in the general case. Does this make sense? It's actually not hugely complicated. Take the same forward kinematics routine that you have. Store the joint axis and the location, and voila, you can populate your Jacobian. You have to wait till you found the tip before you can do it. But basically, that's it. Everyone okay with that? The first time you see it, it's kind of like, huh? Cross product? What? Right? But the Jacobian matrix is really the contribution of joint I on the output velocity. And really what that is the cross product for the linear, and it's just the joint axis for the angular. So I can write my general Jacobian matrix right after I do the inverse kinematics. Right after I do the forward kinematics. So one thing that I'm actually going to suggest, is you compute the Jacobian when you do the Fkin. You want to do it at the same time because that's when you have all the information. Right? It's the same kinematic chain that does it. Okay on that? The only comment now is if I do, here, let me put this up here. You guys okay for a race? Yes.
So you compute the Jacobian when you see the forward kinematics, but it's different for every coordinate that you get?
Yes. But I mean, the forward kinematics depends upon the coordinates that, no, the Jacobian depends on the joint location. The joint location defines your mechanism, which gives you your x and your r or your tip, and it also gives the Jacobian matrix. Right? If you think about it, whoops, as I threw the chalk around. This is x. This is nothing other than dx times dq. So you're getting the location and the slope, if you think of it as a function. So you might as well compute them at the same time. Now, admittedly, you need the Jacobian if you want to solve the inverse in a numerical loop fashion. If I look at this loop, I am iterating, right, over this loop. Notice this is the Fkin of Qi. I need to, every loop, calculate the Fkin of my current guess. Every loop, I need to also calculate the Jacobian of my current guess. And then I update my guess. So the problem, not problem, the feature of this inverse kinematics is that every iteration I do a forward kinematics on my current guess. I calculated the Jacobian on my current guess, and then I update my guess. So this loop means I call the Fkin a gazillion times. So don't think of the Fkin as a node. Think of the Fkin as a library function. Right? And that function will get called 10 times inside this loop. And every time you call it, you also need the Jacobian, so you might as well put it in the same function. Or you can put it in a different function, I don't care. Right? But it's convenient to have it in the same place because they share the same information. Yes?
But you would like to calculate the Jacobian from your real coordinates, like your x, y, and z. But to have these referred with
It's-
guess,
The Jacobian is entirely a function of joint values. It is the same way the tip position is a function. X is a function of Q, right? This is x prime. This is the slope of x. So it is a function of Q.
but they're calculated. Okay, I see.
And this is my guess Q that I then stick in. Then I compare my guess against my desired, which is how I get the error and then move. Right? But you don't need to know the tip location when you're calculating, well, sorry. You need to know the tip in order to calculate that thing inside the Jacobian. But it's all calculated from the joint angles. So that's the generic joint. That is the general Jacobian. The final comment, and our timing is not bad, is to do a custom Jacobian, right? Remember, x dot is equal to jq dot. So if our coordinates are x, y, z, and then theta and phi, and fine, I'll add grip to the end of it. Do you agree that x dot, y dot, z dot, theta dot, phi dot, and g dot is going to be the Jacobian times q0 dot, q1 dot, q2 dot, that these in the top are just going to be j0v, j1v, j2v, etc. Notice that I am including grip. Do you agree that the grip joint is going to have 0 up there, right? Because the grip doesn't actually change the location. Theta, if that is q1 plus q2 plus q3, guess what? I put dots on it, which means my Jacobian matrix is going to be 0, 1, 1, 1, 0, 0, 0. There's too many zeros here, isn't there? If I define my roll angle to be q4 plus sine theta q0, do you agree that phi dot is q4 dot plus sine theta q0 dot plus cosine theta q1 dot plus q2 dot plus q3 dot times q0? Which means I get sine theta cosine theta times q0, cosine theta times q0, cosine theta times q0, and 1, 0. Right? Do you agree for grip? It is just 0, 0, 0, 0, 0, and then I think I called it C. And if you look at it, the Jacobian is basically a 5 by 5, and if you want to add grip to it, make it a 6 by 6. That's your call. Does that make sense? One way or another, you will have X, Y, and Z, which means you need to have kind of the translational components, which is why you definitely want to kind of go through the Fkin and do all of those things. If you want to use the rotation matrix, you can compute the general Jacobian. If you use a custom, basically just compute them. Which means you now have the Jacobian, which means you can stick it in here. And I'll make one final comment so that it is complete. This is my general to compute this error. So I've computed Jacobian, which means I've got a matrix, I can invert that matrix, right? Be careful when you invert the matrix. Hopefully it's well defined. The final comment is error. And the reason I wrote it as error, it is basically the error in translation and the error in orientation, the general error, if I go for the general 6-DOF case, 6-dimensional case. The error in translation is just xd minus x of qi. Easy. How do you compute an error if you're given an r desired and an r actual of my guess? That is the only, please.
Me?
I thought you were gonna.
Oh, okay, yeah, I was. The angle between the two?
Yes, it is. It's not just an angle, it is also, basically this is a rotational, so you need the vector about which you're going to rotate as well. So this is an axis angle kind of thing. So there's a simple formula, which is, and this is why I just want to put up here, it is basically Ex of the actual cross Ex of the desired, plus Ey of the actual cross Ey of the desired, plus Ez of the actual cross Ez of the desired. And you can sit there and think about what that means, but that is actually the formula. So just to be kind of clear, the error is desired minus actual, but it basically means it is RA cross RD. A comes first, actual comes first. So if you want to do the general rotation matrix thing, this is the formula to calculate the error. Right? The error is 6 deep, has translation and rotation the same way the Jacobian matrix has translation and rotation. Probably not what you care about, because if we do custom, then the error is just the error, right? But if we're talking general rotation matrices, you can't just take the difference between rotation matrix. You got to take the rotation vector, so it's the eigenvalue, blah, 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 blah. Please. Okay. Doing a little dance, shaking it up.
And
Yes?
I guess one question that I had back to this algorithm over here, when you take the inverse Jacobian, shouldn't you be applying that on the desired position, not the joint state or whatever that Q is?
So, there's a lot of subtleties and differences, right? You can argue that instead of Newton-Raphson, you take different algorithms and you can tweak this thing. But fundamentally, you calculate a Jacobian at a certain joint location. So this Jacobian is calculated at a joint location, and the best joint location is your best guess. So I'm not sure I'm answering your question. Was that the question?
I guess the Jacobian is a matrix, so
Yes.
don't we need to be applying it on some kind of vector?
Sorry, the error is a vector.
Oh, the error is a vector, okay.
Yes, error is a vector. Right,
Okay.
and the error is this 6-dimensional vector. It is the vector of all coordinates.
Okay.
Apologies. Joint guess is a vector. So this is a vector equation. Please.
Alright, I take it back.
So all of that said, is once you've got the Jacobian, you can actually, instead of just doing the tip command, you can also calculate the tip command velocity, right, which is just J times Q dot. Once you got the Jacobian, you can always calculate X dot as J equals Q dot. Notice the other thing is usually I want there to be a Q dot command here. How do I get that out of IKID? Notice that basically it is just right in here. I can effectively set my Q dot command be J inverse times X dot command. Right, so the Jacobian relates velocities. So you can basically either do a finite difference here and kind of it all works out just fine, but if you want to be particularly particular, you can calculate the velocities using that same Jacobian matrix. And with that, we have basically a full picture. The biggest part of this is, do you compute an IK once and stick it in which case, if you do it once, you probably have to do this iteration, I don't know, 5, 6 times until you converge. Or do the analytic, which I'm still a fan of. If you're doing a tip movement, it means you're calling the IK every single 10 milliseconds, right? Every circle cycle. Guess what? Your guess is going to be really good because it's really close. Which means you probably only do one iteration in this loop. Because you're going to be so close anyways that one iteration is going to get you there. And if you do one iteration, notice that Qi plus 1 minus Qi is going to be divided by dt, and that is your velocity, which is, by the way, Q inverse times, right? I mean, so your velocity you almost get for free because that's the delta of each step. So my point just being is, if you put this part of the servo loop, don't make it an infinite number of iterations. Don't make it a while loop. Because your guess is going to be so good, just make it one iteration and you're done. And it'll be just fine. But that sets up the entire picture. What it really comes down to is you got to go through the kinematic chain, which is why we started there, because you need it to get the Jacobian matrix, you need it to get the position, et cetera, et cetera. You want to pick the custom coordinates, probably. That means you're going to define your Jacobian for what it is you have. And then basically, it's implementing that kind of block diagram. And then what we'll do next week, so yes, I'd love for this to work this week. There's so many occasions and scenarios where this can fail, so let's try to make it work. If it doesn't, we'll debug it, we'll fix it next week. But what we'll add next week is we'll put a camera on, which will give us the actual target XYZs. So for this week, what I'd love to do is actually put a masking tape on the table, take out the ruler, measure that point. It is 30 centimeters over, 5 centimeters there, right? Enter those coordinates, arm should go there. Next week, hopefully, we'll do it with the camera, and the camera will tell us where that is, and then voila, we're well on our way to picking up objects. So that is probably as much as I want to talk about kinematics, which is plenty. It is kind of at the core of everything we do. Once we have this debugged, everything is now going to be at a slightly higher level of just specifying goals. And all this movement stuff will then happen inside of that block. So it is a big, important block. And with that said, it is totally exciting to see this happen. I am very excited for Friday to start seeing the hardware move. And I realize going from a 2 DOF to a 5 DOF with inverse kinematics and coordinates is a big jump. So let us know if you run into issues. I'll definitely be around Thursday night. But otherwise, I'll see you guys Friday.
So since this node is probably just going to be slotted in, Well, I mean, there's no reason to write this node this week and then write it poorly so then we can't use it in the future.
So it should be well.
I think we might as well just write this one in C++.
Yeah,
Like,
sure.
especially if we want to, like, just
I'm just not